let's talk about the different types of decay that can happen. So there are 5 different ways that we are going to discuss that radioactive isotopes can decay. There's alpha, beta, gamma decay, and then positron emission and K capture. We're going to look at each one of these individually here, but before we do that, a little bit of nomenclature here, just to give you a heads up as to what we're going to be seeing for the rest of these different kinds of radioactive decay. It's going to be involving these different particles here. So we're going to be looking at alpha particles that have this symbol, and all these symbols are working on the same kind of framework as the chemical symbols that we saw before, where the mass number is up and to the left, and the atomic number is down and to the left. So an alpha particle, as we'll see in just a second, has 2 protons and 2 neutrons, which gives it 2 and 4 as its numbers. And as we work through the rest of these, we're going to be seeing how we'll have different particles that have no mass number. That's not because they have no mass at all, it just means that they have no protons or neutrons. Because remember, the mass number is the protons and neutrons added together. So a beta particle, for example, is actually an electron, as we'll see later on. So it has no mass number, but it does have the same charge as a proton, just opposite in sign, and so we're going to give it a -1 atomic number. And so we'll go through the rest of these as we go through the types of decay, but I did want to put this in here for a reference for you so you can go back to this when you're studying or when you are working through the homework. So the first kind of decay here is alpha decay. This is the loss of an alpha particle, which is the same as a helium nucleus, just really, really energetic. Really high energy helium nucleus. It has 2 protons and 2 neutrons, just like I mentioned a second ago, which gives it the symbol He 4 and 2. Sometimes, excuse me, sometimes it is written as the actual alpha symbol. I'll kind of go back and forth as to which one I use. Either one is fine. When something undergoes alpha decay, what that tells you is that the thing that's decaying is very large. The only stuff that undergoes alpha decay, those are isotopes that are so big they actually need to lose mass in order to become stable. Other isotopes that we'll see later on, it's not so much the mass of the nucleus is making it unstable, it's the relative numbers of protons and neutrons is making it unstable. But with really, really large isotopes, there's no ratio of protons to neutrons that's stable. It needs to get rid of some mass. And so those will undergo alpha decay. This is actually the only kind of decay that loses mass. All the rest of the types of decay that we're going to see, the mass number will actually never change. It's just the relative numbers of protons and neutrons that change. But for alpha decay, you do actually lose mass, as we can see here. So we have uranium-238. It will decay to thorium-234 and give off a helium nucleus or an alpha particle. So one thing I want to point out here, and this is going to be true again for all of the radioactive decay that we're going to see, the mass numbers on the left side of the arrow will always equal the mass numbers on the right side of the arrow when you sum them. So we have 238 on the left, 234 plus 4 gives us 238. The atomic numbers, same thing. They will always sum to the same value. So we have 92 on the left, 90 plus 2 on the right gives us 92. So this is going to be our key, the way we're going to determine what is being created, what we're going to call daughter nuclides are when a nuclear decay happens. So as an example here, we're going to write the nuclear equation for the alpha decay of radon-224. So radon, or actually, sorry, that's radium. I always get those two mixed up. Radium-224. If we look at radium on the periodic table, Radium is element number 88, so it's going to have 88 protons. If it is undergoing alpha decay, that means that we know one of the products of this decay is that. It's an alpha particle. It has to be, otherwise it's not alpha decay. So we already know one of the products, and so then to figure out what the other product is, it's just simple subtraction. So if we started with 224, we lost 4 of it to the helium here, then that means the other product has to have 220 as its mass number. And if we started with 88 and we lost 2, that means that we're going to be down to 86. And if we look at the periodic table, that is radon. So radium turned into radon. And that is the nuclear equation for that particular decay. It's pretty straightforward, just simple math, and it's not going to get any more complicated than this, pretty much. The only thing that's going to become more complicated is when we're doing different types of decay, this thing will be different. So it's not going to be this every single time, but the overall process is going to be exactly the same for everything. So the next type of decay we're going to look at is beta decay. This is when a nucleus spits out a high energy electron. So the nucleus is unstable. It spits out a high energy electron. And as a result of that, let me see, do I have? No, I don't. What happens is one of the neutrons in the nucleus actually, literally, turns into a proton as a result of this, which is something we've never seen before, but this does happen all the time. You have a neutron spits out an electron, a very high energy electron, and because the neutron, which was neutrally charged, loses negative charge, it becomes positively charged. And so we actually have a neutron turning into a proton. This can be written either as a beta symbol or an E. Either one is fine. But the symbol, the numbers that go along with the symbol are always 0 and -1. So we're not changing the mass number because we didn't lose protons and neutrons. We didn't lose the total number of protons and neutrons. We did turn a neutron into a proton. But since the mass number is the protons and neutrons added together, we didn't actually lose any mass in that sense. Technically speaking, we did lose a tiny bit of mass because the electron does have a tiny bit of mass. But in terms of the mass number, we did not lose any. And then the atomic number is going to increase because once again here, the atomic number on the left side of the arrow needs to equal the atomic numbers on the right side of the arrow added together, and it does indeed do that. We have 54 plus -1 is 53. And we'll see an example, we'll do examples of those once we get through the rest of these different types of decay. The next kind of decay here is gamma emission. This one is unique because we're not actually losing a particle. At least in the traditional sense of losing a particle. Technically, photons are particles, but we are losing high-energy light. High-energy radiation is what is being emitted by the nucleus in this case. So it actually is 0 in terms of both its mass number and its atomic number. So it has no charge in terms of electromagnetic charge. Is not positive or negative. It's just a photon, and it has no mass in terms of the mass number because it's not a proton or a neutron. But regardless of that, it is very dangerous. Gamma rays are the highest energy light possible, and if you live in the Marvel universe, they will either kill you or turn you into the Hulk. That is in the Marvel Cinematic Universe. He was exposed to gamma radiation. He got turned into the Hulk. In our universe, it will just kill you. No hulkiness to be gained. just lots of death. So gamma radiation, very dangerous, very, very high energy light. So it doesn't actually change the mass number or the atomic number. Positron emission is the next way that a radioactive isotope can decay. And positron emission is essentially the exact opposite of beta decay, because what you're losing in positron emission has the exact same mass as an electron and has the exact same charge as an electron. It's just positive instead of negative. So a positron is essentially a positive electron, is what it is. It's a positively charged electron. And so when you lose a positron from the nucleus of an unstable isotope, a proton gets turned into a neutron. So now we're going back the other way. Again, this is just the opposite of what happened in beta decay. And so in this case, once again, the mass number does not change because the positron does not have mass compared to protons and neutrons, but the atomic number will change. So in the example here, we have carbon 11 has 6 protons. When it undergoes positron emission, because carbon 11 is most certainly not stable, it turns into boron 11, and it releases that positron. Positrons, by the way, do not last long. Positrons, when they hit electrons, which there are electrons everywhere, everywhere. As soon as that positron is emitted, like within microseconds, it will bump into an electron and they will annihilate each other quite energetically. And you'll get a big gamma burst as a result of that, which we'll talk about a little bit more when we get to PET scans, because that's actually how PET scans work. You put a positron emitter inside your body, and then you get to shoot gamma rays from inside your body, which is kind of cool and kind of crazy at the same time. So that is positron emission, and like I said, we'll do examples of some of these in just a minute. The last one here is electron capture, also known as K capture, because for some reason nuclear scientists refer to the 1s electrons as K electrons. So if you remember from Chem 1 and the electron configurations, 1s is the lowest energy possible orbital for everything. Everything has a 1s orbital, and that is the lowest energy possible for the electrons to sit in. And in electron capture, the nucleus that is unstable, so if this is our nucleus here, and here's our 1s orbital, and there's an electron right there, the nucleus sucks in that 1s electron. So it's not that there's, an electron zipping past the nucleus and it grabs it as it goes by. It's an electron that is in the 1s. It's from the atom itself. And so it sucks in that electron and it turns a proton into a neutron. So this is, in the end, the same result as positron emission, a proton turning into a neutron, but it is a different process. There's a different method for this happening. And by the way, electron capture also tends to be quite dangerous. Well, they're all dangerous, but if it seems like, oh, it just captured an electron, there shouldn't be any radiation from that. And no, this is accompanied by some gamma rays. Because when you capture that electron and turn that proton into a neutron, the nucleus is almost like an electron configuration, where as soon as you change the number of things, it has to rearrange itself. And so when the nucleus kind of shifts around a little bit, there's enormous energies associated with shifting the particles in the nucleus. And so you could get some gamma rays released from that. And also, because there's now a vacancy in the 1s, you'll have some electron that was in a higher orbital drop down to take its place, and that usually also produces dangerous radiation because it's a big drop. from really almost any other electron orbital down to the 1s. At the very least, it's going to give off UV radiation, which is not terribly dangerous, but can damage biological tissue. If it drops from higher than the 2s, you could get more dangerous. You could get up to X-ray type energies, just depending on how far the electron has to drop. But the more dangerous radiation comes from that rearrangement of the nucleus. All right, let's do a few examples here, and then we will call it for this video. So the first example here, we're going to do the beta decay of berkelium-249. And actually, why don't you pause the video here and try to work out these yourself, and then come back, and I'll work through them with you. So pause the video here. Alright, so the first example here, we have berkelium-249. The number after the element here is always going to be the mass number. If we look up berkelium in the periodic table, it's going to be way down at the bottom of the periodic table. It is element number 97. If it is undergoing beta decay, that means that one of our products has to be this. And again, you could also write that as a beta symbol. I prefer to just put the E. So that has to be one of our products. The mass number is not going to change, because remember, the mass number only changes with alpha decay. The atomic number is going to change, though. So we lost an electron, so that means that we are going to turn a neutron into a proton, which means we're going to have 98. And again, the other way of thinking of that, if you don't want to think about it in terms of this turning into that, you can go the math route. We have 97 on the left, we need 97 on the right. To get 97 with already knowing that we have -1, this has to be 98. And if you look at element number 98, that is CF, which is californium. Berkelium is named after Berkeley, California. Californium is named after California. So we have one thing named after something in California turning into another thing named after California, which is kind of interesting. Part B, we have oxygen, 15. Oxygen is element number 8 on the periodic table. And that is undergoing positron emission. So we know one of our products is this. So it has the same symbol as an electron, but it's positively charged instead of negatively charged. Again, the mass number is not changing. It only changes with alpha decay. The atomic number, if we're going to have 8 total on the right, since we have 8 total on the left, has to be 7. 7 plus 1 gives us 8. And that is nitrogen. So that is the nuclear decay equation for the positron emission of oxygen-15. The last one here, it's going to be a little bit different. We have iodine-111. Iodine, by the way, is element number 53. This is going to be a little bit different because this is the one type of nuclear equation where we actually have 2 reactants and only 1 product. And actually the neutron here. Our product is going to be different than just a neutron. But we're going to have 2 reactants and 1 product because we are adding something to the nucleus instead of spitting something out. So we're going to have iodine-111 plus an electron. So we're adding an electron to iodine-111. The 111 is not going to change. Again, the mass number is not changing except for with alpha decay. But now we're taking 53, we're adding an electron to it, which means we're going to lose one of those protons. And so we're going to have 52, which is tellurium. That is the electron capture of iodine 111. Alright, so there's another handy little table here for you to use as you're studying and as you're working through the homework. It's a nice little guide for what happens in each of these different situations. So there's just a generic nuclear equation here, how it can be represented graphically, and then how it changes the mass and atomic number for the daughter nuclide that is created. So we'll call it there for this one. In the next one, we're going to pick up talking about ionizing power versus penetrating power. So I'll see you all in the next video.